Diffraction gratings are somewhat unfortunately named because they're really just multiple slit setups with a great number of slits, which are very closely spaced. So everything that we took away from our analysis of multiple slit interference can be applied to diffraction gratings. You might want to think of them as being interference gratings. And what we're looking at here is a visualization of the interference pattern on the opposite side of a diffraction grating. Here's the incident laser beam, most likely. And you can see there's a whole bunch of dots here indicating closely spaced slits. One of the features that pops out here is just how spread out the interference maxima are. The red bars show you the bright fringes. So if you put a screen over here, this would be a bright fringe, and a whole bunch of secondary maxima in between, which are so low in intensity that we don't even see them. You will recall, this is the slide that we used to look at the geometry of multiple slit interference. The screen is much farther away from the slits compared to the separation between the slits. And when we look at a particular point on the screen, we can assign it a coordinate y. That's the distance between that point and the point on the screen, which is directly in front of the, I'll say, the center of the slit pattern. We call that angle theta. Previously, in most cases, theta was a small number because all of the bright fringes that we looked at were close to the forward direction. We'll see that that's not necessarily the case anymore for diffraction gratings. And when you zoom in on the slit pattern, again, this distance, the slit separation, is very small compared to the distance to the screen. And that means that in an up-close view like this, each of the rays meeting at a particular point are essentially parallel. These rays look parallel, but they really do meet at some point far away. And we found that the path length difference for the waves from adjacent slits, all meeting at that one point at the screen, that path length difference can be expressed in terms of the angle at which you're looking on the screen and the slit separation. And we found that, you know, you can see it in the diagram here, that delta R is going to be the same for each adjacent pair. Okay, the only thing we have to change about the picture is just to increase the number of slits. So a great many slits, and the separation between them is even smaller than it was before. And I've been careful here to indicate the wavelength. These vertical lines within the laser beam indicate the crest to crest difference, which is what we call the wavelength. And I made sure to make that distance less than the separation between slits. So I'm indicating with the pointer here, lowercase d, this distance from one slit to the next is greater than the wavelength of light. And we'll see that that is necessary to get any kind of diffraction pattern. If the wavelength were actually greater than the slit separation, then you would not see a set of maxima. You'd really just have that one central maximum in the forward direction. Now, maybe you're wondering, how on earth could you create a multiple slit setup with such a tiny separation between the slits? You know, is this something that you actually encounter? Well, I don't know how it's done, but yes, diffraction gratings have been around for a while, and it's impressive just how small the slit separation can be now. I mean, we're talking nanometers. Here's an older image. If I had to guess, I would say there's something like 10 to 20 slits over a space of only 1 micrometer. 1 micrometer, you'll remember, is about 1/50th the width of a human hair. So this distance is already 1/50th the diameter of a human hair, and yet we've got 10 to 20 lines crammed in there. So these are really closely spaced. Here we've got an electron microscope image up close of that diffraction grating. It's impressive how regular the structure is. So these things can be manufactured. A laboratory diffraction grating, you know, for the purposes of education, looks something like this. And usually it will state the number of lines per millimeter or lines per inch. So that's not exactly lowercase d. We can calculate lowercase d from that, but that's usually how it's stated. Rather than giving the slit separation in SI units, they give us the number of lines per unit distance, and it's often not in SI. For instance, the millimeter is not the SI unit of distance. Often it's given in terms of the inch. So there's some conversion required. These are really closely spaced. And maybe you're noticing it's not quite slits, is it? It's not necessarily an opaque barrier that's had slits cut into it. That's even more true if you're talking about a reflection grating. So here you'd have an incoming plane wave or laser beam incident upon this array of teeth or ridges, and the light reflects from those ridges. But once it's been reflected, it's basically equivalent to an actual set of slits. It doesn't really matter why you've got multiple waves traveling outwards from a regularly spaced set of points. It doesn't matter whether it's light passing through slits or light bouncing off ridges. The effect is the same once the light has been reflected or passed through the slits. The geometry after reflection is the same as the geometry after passing through slits. I say the same, but that's not totally true. You would have to use a diagram like this to analyze the directions of constructive interference for light passing off of these ridges here. And we may look at this later. I'll point out that if you're trying to actually glean some information from this diagram, they could have improved the angle here. This is supposed to be perpendicular. This ray doesn't really look perpendicular to this one. But you can use right triangles here to find the path length difference for two of these reflected rays. So each of these ridges reflects an incoming wave, and that acts like a single slit. So diffraction grating, reflection grating, in fact, sometimes it's called a reflective diffraction grating. It's all interference. All of these are just basically multiple slit interference sources. And it's not just manufacturing that produces these diffraction gratings. They tend to exist in nature as well. So there's a lot of familiar phenomena that you can explain, visual phenomena that you can explain using the diffraction grating. Anytime you encounter iridescence in nature, and I shouldn't say anytime, because we've looked at soap bubbles, the iridescence of soap bubbles, that's really a thin film interference phenomenon. This is different. You can do some Googling and pull up all kinds of images like this, but if you look at the feathers up close, or not so much the feathers, but the barbs that make up the feathers, I think one of these would be called a barb, and it's got a rich structure under a microscope. And then the barb has barbules on it. I don't know the details, but check it out. You've got a regularly spaced array of barbules or crystals that conceivably could act a lot like a diffraction grating. This one makes it even more clear. So we can contrast the microscopic structure of, I'm going to call them barbules. It looks like they took a cross section, so they cut open one of the small units of structure of these feathers, and you can see that in a mature adult feather, there's this regular array of some kind of, I don't know what that's made out of. We don't need to know the details from a biological perspective, but light reflecting off of that structure is going to behave a lot like light passing through a multiple slit setup. And then over here with this white feather, you don't see that same kind of regularity. So almost immediately we can recognize why you would expect to see a diffraction phenomenon for this type of barb or barbule, but not so much from this one. Recall from our analysis of multiple slit interference, each particular wavelength has its interference maxima in a corresponding set of directions. So if you change the wavelength, then the directions in which you get constructive interference will also change. So That helps you understand why, as you move your head around a source of uh, or something that looks iridescent, you might expect to see different colors at different angles. Now, that doesn't quite explain this feather, because I think with the peacock feather, no matter where you're looking from, the eye of the feather is going to look the same color. But it does help explain, oh, by the way, here's another electron micrograph of a peacock feather way up close, a lot like a diffraction grating. Anyway, the business about looking from different angles would help you explain something like the iridescence of a beetle. I think I recall from my own experience that if you were to put your head in different positions, the color pattern coming off of the beetle's shell might change. And this is not a micrograph, so it's not obvious, but if you were to zoom in on the beetle's shell, you would probably find a microscopic array of ridges that act a lot like a reflection grating. Pretty clever beetle there. This one surprised me. Here's a fish tank. Well, we're looking at the exterior of a fish tank, which has a biofilm on the surface. So that's a whole bunch of germs, little germies. And germs are really small. Bacteria, they're on the order of a micrometer. So if you've got enough of them arranged in rows, I looked for an image of bacteria in rows under a microscope, couldn't find a sufficiently regular one. But if that happens, you might expect the bacteria to behave like a diffraction grating or reflection grating. So that's why we're seeing different colors in different positions. And presumably, if you were to move your head around in the vicinity of the fish tank, you would see different colors from different angles. That means you're seeing the interference maxima corresponding to different wavelengths at those different angles. The first thing we should check then is whether or not this small angle approximation that we've been using still works for diffraction gratings. We talked about the fact that theta is basically the same as the sine of theta is the same as tangent of theta, which was y over L. All of those numbers were really close together for typical multiple slit setups. But now we're talking about a great number of slits that are really closely spaced. So let's look at an example. Here's a grating that's advertising over 25,000 lines per inch. That's not SI units, so let's first convert. And let's assume that we're talking about a wavelength in the middle of the visible spectrum. Okay, well, 25,400 lines per inch. By the way, this number is suspiciously reminiscent of 2.54, which is the conversion from inches to centimeters. I know that 1 inch is exactly 2.54 centimeters. So that's probably why this number is popping up. Okay, so 1 inch, I've put in the numerator to cancel the inch down here. 1 inch is exactly 2.54 centimeters. So we can cross out the inches and we get this 1 million lines per meter. And I emphasized that we're working with at least 1, 2, 3 significant digits here. So I added some zeros after the decimal point. Okay, well, you could probably do this in your head. If you've got 1 million lines per meter, how many lines would you have per millimeter? 1 millimeter is only 1,000th of a meter. So 1 million lines per millimeter, 1 million lines per meter, just divide that down by 1,000. And you could actually call this 1,000 lines per millimeter. So instead of 25,400 lines per inch, you could say 1,000 lines per millimeter, or just keep everything in SI. And what did I do here? I just took the reciprocal, right? If this isn't clear to you, pick some much easier numbers. Like, what if you had just 5 lines per millimeter? That's easy to visualize. A millimeter is it's not a very large distance. If you had 5 lines per millimeter, wouldn't the distance between each pair of lines, adjacent lines, be 1/5 of a millimeter? Those are reciprocal. So all you have to do is take the number of lines per millimeter and do the reciprocal. That is D, but you have to be observant of your units. So the reciprocal of 1 million is 1 millionth, but my units here are meters. So 1 millionth of a meter is the separation between lines here. A millionth of a meter, that's a micrometer or micron. So I could also express lowercase d that way. 1 micrometer. That's 1/50th, typically, the diameter of a human hair. It also happens to be double the wavelength of visible light. So if I round this down to 500 nanometers is actually 0.5 micrometers, 0.5 compared to 1. So we're talking about a slit separation that's roughly double the wavelength of visible light, or green light, let's say. Here's another common diffraction grating that you would buy for educational classes, you know, well, a class like this, 1,000 lines per millimeter. So this actually happens to be the same spacing as this one. The only difference is the units used. Instead of lines per inch, if you put it into lines per millimeter, you get the same number. And you can't see it here, but there are lines etched into this transparent film. Again, I don't know the details. I tried to find an image under a microscope of this type of grating. Couldn't find it on the web. Okay, let's review units briefly. A micrometer is a millionth of a meter. And why don't we do this? Let's move the decimal place 3 to the right, which is multiplying by 1,000. And we pay for that by decreasing the power of 10 by 3 from -6 to -9. So I could also write this as 1,000 10 to the -9th meters. This is a billionth of a meter. That's what we call a nanometer. So 1 micrometer is 1,000 nanometers. I didn't actually write that here, but 1,000 you should really memorize that, because as we deal with these diffraction grating problems, numbers of this order of magnitude come up often. So try to memorize that 1 micrometer is 1,000 times as great as 1 nanometer. Okay, well, we're very familiar with the condition for constructive interference. We've already looked at the geometry. If you want constructive interference between the waves from 2 adjacent slits, then this is the condition that must be satisfied. And of course, that's true for any adjacent slit. So really, it's the condition for constructive interference from all of the waves. That's kind of cool to think about. If you're talking about 1,000, 2,000 slits, there are particular directions given by this formula at which all of those waves interfere constructively. So you would expect a large total amplitude compared to the amplitude from just one slit. And notice I'm labeling the angle theta with an index m. So a particular integer value of m over here corresponds to a particular angle. You need the path length difference from adjacent slits to be 1 wavelength, or 2 wavelengths, or 3 wavelengths, etc., if you want constructive interference from all the arriving waves. And this condition, I'll remind you, came from assuming an inherent phase difference of 0. All of these slits are being illuminated by the same laser, so we're not worried about any inherent phase shift from one slit to the next. Now, this is just vocabulary. I'm being precise here with the language. We're looking for the directions in which all of the waves from all the slits interfere constructively. Well, we're going to see that that's really the only direction in which you get any significant light intensity. All the other directions experience perfect, or I should say maximum destructive interference, or something really close to max destructive interference. So effectively, these are the only directions in which you get light. Just think back to the previous presentation when we looked at graphs of intensity versus position for increasing numbers of slits. All of those secondary maxima get squashed down more and more. And by the time you've gotten 100 slits or 1,000 slits, there's effectively no light intensity going in any direction except for the primary maxima. So those directions are the directions in which we say the light is diffracted. Okay? Again, what's the difference between diffraction and interference? It's really just a historical attachment to terms. All of it is an interference phenomenon, or you could say superposition. But when you're talking specifically about a diffraction grating, you know, something that was manufactured with the separation so small you can only see it under a microscope, then we say that that's the direction in which the light is diffracted. Let's evaluate theta 1. That's the angle for the what's called the first order of diffraction, first diffraction order. In other words, all the waves from all those slits arriving at that point P on the screen have a path length difference of 1 wavelength between adjacent slits. So do this in your head. Move D over to the other side, plug in 1 for M, take the inverse sign or the arc sign to isolate theta, or theta 1, I should say, and you find that theta 1 is merely the arc sign of lambda over D. I find this pretty easy to memorize because we've been talking for a while now about this very meaningful ratio. How does the wavelength compare to the slit separation? And here's where that fact comes in that I mentioned a moment ago. In my picture, I was careful to make sure that the wavelength of the laser beam, that crest to crest distance, was less than the slit separation, because we need to be taking the arc sign of a ratio less than 1. If you ask a calculator for the arc sign of a number like 1.5 or 2, you'll get usually an error message, because no real number greater than 1 has, no, I should say no number greater than 1 has a real arc sign. Remember, arc sign is the inverse function of sine. So when you plug an angle into the sine function, you get a ratio, that's what comes out, between -1 and 1. So real angles have sines equal to some number between -1 and 1. You'd never plug an angle into the sine function, a real angle, and get a sine that was greater than 1. So if you flip that inside out, you can't ask for the inverse sign of a number greater than 1 and expect to get a real angle. Now, I've mentioned that you can talk about imaginary outputs or complex outputs of the sine function, but that doesn't help us for this purpose. So if you expect to get an angle out, then the wavelength needs to be less than the slit separation. And now they're getting close together. D is so small now that it's almost as small as lambda. That was never a concern before. For the multiple slits where the slit separation was, 1/10 of a millimeter, a 20th of a millimeter, that's really small to the human eye, but it's still much larger than, or significantly larger than, the wavelength of light. Now we're talking about a slit separation so small, it's almost as small as a wavelength of light. Okay. Well, for this particular example, 550 nanometers compared to the slit separation of 1,000, that was the same as 25,400 lines per inch. This ratio is close to 1/2, right? So what angle has a sine roughly equal to 1/2? Well, we know that the sine of 30 degrees is 1/2. So this angle we expect to be close to 30. Definitely not a small angle. If we think back to the small angle approximation, you can only say that sine of x and tangent of x and x are the same, roughly the same, if you're talking about angles less than something like 10 degrees or 15 degrees. See how the curves are all very close together for 15 degrees or less, I'll say. By the time you get to 33 degrees, right about here, there's significant divergence of these functions. So it's no longer valid to use the small angle approximation. If you were going to use this formula to predict where on the screen you would look to find a bright fringe, and you replaced the sine of theta by the tangent of theta, which is that coordinate y over the screen distance L, you're going to get the wrong value. You will not very accurately predict the location of the bright fringes. So we really need to use the sine function from here on out when we're talking about diffraction gratings. There's some special terminology that's used in spectroscopy. Rather than refer to this as the first interference maximum on either side, it's called the first diffraction order. So when you hear that word order, they're really just talking about which of the bright fringes. We don't even really call them fringes. They're so far spaced, it doesn't really even look like a multiple slit interference pattern at that point. Those bright spots are really far apart, so we refer to them as orders. And how many of the orders you see depends on the ratio between the wavelength and the slit. It could be that you see 7 of them, let's say, or sometimes you only see this central one. It's possible to not see even the first diffraction order. So let's continue with the example we've been using and see how many diffraction orders would actually be visible with this diffraction grating. Well, I've already shown you the formula for theta sub m. Again, that comes from d sine theta. It must equal an integer number of wavelengths. Let's evaluate this formula for the first several integers. If we plug in m equals 1, the 1,000 nanometer separation between the slits and the wavelength of, I think this is green light. And you'll notice I didn't even write nanometers over nanometers because they would just cancel anyway. You're always plugging a dimensionless quantity into the sine or arcsine function. Okay, since the first diffraction order is at 33 degrees, you might guess that the next one is going to be at something like 66 degrees. However, the sine function or the arcsine function is not linear anymore as you move away from the origin. If you picture the sine function in your mind, near the origin, it kind of looks like a 45-degree line, right? But as you move away from 0 degrees, it begins to bend downwards. So it's not necessarily going to be 66 degrees. In fact, when you take the arcsine of 2 times basically 1/2, isn't this number already greater than 1? This is a ratio greater than 0.5. So when you multiply by 2, you get a number greater than 1. You can't ask the calculator for the arcsine of a number greater than 1 and expect to get a real angle. There is no real angle whose sine is greater than 1. So this comes out undefined. And what this is telling us is if you shine light of this wavelength through the diffraction grating, you're only going to see one diffraction order, just that first one off at 33 degrees on either side. You won't see the higher diffraction orders. Here's a picture of an old-fashioned spectrometer, it's called, that uses a diffraction grating. And it's very common to still use these in physics laboratories, but nowadays, if you're doing real spectroscopy, you're going to use more sophisticated instruments and modern electronics for determining the wavelength of light. But these are still used in labs. We've got a diffraction grating mounted on a pedestal here. And this is basically a telescope. You've got some lenses in here probably, and you could send some laser light into this tube here, or even look at the light coming out of a lamp and collimate it in the tube, like a sodium lamp, or even an incandescent bulb. That light is passed through the diffraction grating, and we say it diffracts at particular angles, which we've just calculated, depending on the wavelength and the spacing. And one of these tubes, optical tubes, usually can be swiveled around the pedestal. It doesn't look like this is constructed that way, but the ones I've used have basically a protractor, or all the angles are marked around the perimeter here, the circumference of that pedestal, and one of these tubes can be swiveled around. So you move the tube around until it lines up with one of those diffraction orders, and then you just read the angle right off the pedestal there. So if you know the angle and you happen to know the slit separation, you can use the formula we looked at to very easily calculate the wavelength of light. So this was an often used tool for many years in spectroscopy. These were around in the 1800s. And previously, but before they were able to manufacture modern diffraction gratings with that super small slit separation, a prism was actually placed here. So a piece of glass was used to refract or bend light, and the amount of the bending depended on the color or the wavelength. And that's a totally different phenomenon. That's really something that can be explained with ray optics, which is the next topic in our curriculum. Right now, we're talking about the diffraction phenomenon. Let's look at some of these educational or classroom diffraction gratings in action here.
This is the 3-laser array with the red, green, and blue lasers passing through a diffraction grating. So these set screws here on the front block are to turn the lasers on and off. And you really don't need very much pressure at all to turn these lasers on and off. So you really only want to turn them till the laser turns on, and be pretty gentle with them in general. These set screws here are to adjust the aim of the laser. You probably won't need to be moving these too much unless you're changing out the battery or something's just misaligned. And this diffraction grating can be swapped out. Right now I have in 500 lines per millimeter, and that seems to be producing a good angle for presentation. More lines per mm means greater diffraction angle. This is just to show you the 3 laser array in action. So you would just align it, set it up, and be gentle with these guys, and just turn these lasers.
Okay, what are we looking at here? For the blue light, I count 1, 2 diffraction orders. Oops, I think there's a third one over here. It's tough to confirm because the other one would be off screen, but at the very minimum, we've got 2 diffraction orders. For the green, same thing, I see 2. And for red, I only see 1. It's possible that the second one is off screen. So maybe if you were to calculate the diffraction angles for red light, you would find that your third one came out undefined, or your second one. So we're already seeing that a diffraction grating can separate white light through this phenomenon of interference. And I'd like to get a little philosophical here and ask you to think about the following. To somebody who had not studied wave interference or light, it would seem very clear that this diffraction grating only sends light in certain directions. Here, here, and here for blue light. And you might think of the diffraction grating as not sending anything, any kind of information or energy into other directions. But we know from our study of interference that each of the slits in the diffraction grating could be thought of as sending out a circular wave with the wavefront that crosses all directions. So if it were just one slit, you would expect to see light across this region. It wouldn't just be here or here. You would see light in all directions. I should qualify that because soon we're going to look at the diffraction pattern from a single slit, and we'll see even there you do find maxima and minima, but the central maximum can be very broad. So you have to ask yourself, is there an actual physical quantity which exists between the bright spots? We know that there's an electric field, or that's how we model it, at least according to the theory. There is an electric field at this point, let's say, from each of those slits. Maybe there's 1,000 slits in there. Obviously, the diffraction grating is much wider than the laser beam. So let's just think about the slits that are actually being illuminated by the beam. Maybe that's something like 500 slits. So there should be an electric field right here from each of those slits. That's 500 different electric fields. And yet they all interfere destructively at all points within the diffraction orders. And that begs the question, is it possible to detect that individual electric field? Like, are we just imagining this, or does it really work that way? If there really is an electric field from each slit at that point, is there some way to confirm that? Well, as I understand it, there's not. The only physical quantity you can measure is the total electric field, because it's the total electric field that gives intensity. The intensity is what we're, in effect, measuring with our eyeballs. Of course, you could also detect it with a CCD or some other device, photographic film. But is it possible to detect the electric field from each individual slit? Because if it's not, then it makes you wonder, is it really even a thing? Is it a real physical quantity? Is our theory even, is it true? Like, does light really work that way? Well, I guess the best we can say is it allows us to correctly predict the interference pattern. So I think it's fun to ponder the existence of those electric fields from each slit, which exist between the interference maxima, and yet there's no way to measure them individually. The only way we can convince ourselves of their existence is the fact that we have correctly accounted for the interference pattern. We're back here with Professor Boyd, the necktie guy, and this particular video is a little bit longer, but it's very informative, so I'll just let this run.
This is one of our funnest demonstrations to show atomic spectra. I'm going to show the spectrum of a an incandescent bulb, which is continuous. And then I'm going to show the spectra of 4 different elements: mercury, nitrogen, neon, and especially hydrogen. Hydrogen will be important in the labs and in many other applications. So to show a spectrum, what we use is called a diffraction grating. This looks like a piece of clear plastic, but it's not. It is actually a piece of clear plastic on which an image has been inscribed with dark line, clear line, dark line, clear line, with about 10 to 13,000 lines per inch. So it's called a grating, just like a street grate. It has lines through it. And this allows you to resolve the spectrum of a source of light in the same way that a prism will resolve a spectrum. So what we're going to do is to place this diffraction grating in front of a camera and show you the view of this continuous source with the diffraction grating in place. And what you'll see in the image is the image of the incandescent bulb itself, and then to the right and to the left you'll see a rainbow spectrum that shows what wavelengths are present.
Are you also wondering, like me, what's with the gaps here? Well, we know that each color in the visible spectrum has its m=1 diffraction order, and then over here we can see the m=2 diffraction order for blue. Presumably the other colors would have their m=2 diffraction orders off screen, but why don't we see anything here? What would be beyond red? Well, that's what you might call infrared. So certainly there are other wavelengths being emitted by this incandescent bulb. In fact, if I recall correctly, an incandescent bulb actually only puts 10% of its output power into visible light, 10 or 15%. It's very inefficient as far as producing light is concerned. The rest of the radiation coming out of the light bulb would actually be in the infrared part of the spectrum. So there are definitely other wavelengths which have their diffraction orders right here. Also right here, there might be a little bit of UV light coming off of the light bulb as well. I mean, there's no reason why it should cut off so abruptly. Now beyond blue, there would be violet, but the human eye is not very sensitive to violet light, and that may be why you're not seeing it. I mean, the camera may have picked up some of it, but then, you know, the violet light coming off of the computer screen, I guess, is weak enough that we don't really detect it. I'm not sure how that works, but if you were actually in the room observing this demonstration, a rattlesnake, for instance, maybe not a rattlesnake, but these pit vipers that are sensitive to infrared, they would actually detect energy in this direction. And an insect that could see ultraviolet light would probably also detect energy over on this side.
In this, you'll see as you look on the right side, violet through all the colors of the spectrum, all the way through red. So that's a continuous spectrum. We'll try next to look at a discrete spectrum of mercury. Now what this is it's a discharge tube. It has mercury in it, and what I'll do is energize this tube, apply a voltage to the tube, and that causes the gas in it to emit spectral lines according to the spectrum of the element that we're using, in this case mercury. So I'm going to locate this, its proper spot, turn off the continuous spectrum. So this is a mercury spectrum without the diffraction grating. And let me get it in focus here. It's a bluish colored spectrum. There are mercury vapor lights that are used as street lights. So this may look similar to this bluish tint to the mercury vapor. Now let's try it with the diffraction grating in place. And what you see in this case are a green line and a blue line predominantly in this mercury spectrum.
Okay, so for blue, here's the M equals 1, or first diffraction order, second diffraction order. Here's the first diffraction order for green. Now this cannot be the second order for green because we've already seen how the arcsine function works. That would put the second order somewhere out here, past the second order for blue. So this must be some other color, some other wavelength that happens to look similar to this first green here. So hopefully you're already thinking, why does this pure mercury, the single element vapor, produce only a discrete set of wavelengths rather than the continuous rainbow that we saw from the incandescent bulb? And that's something that we will be able to partially explain by the end of the semester.
Next, we will try a nitrogen spectrum. I'm using this fur to prevent burning flesh. So this is nitrogen spectrum. And with the diffraction grating in place, we see a number of lines present, some red, orange, yellow, green, and a violet turquoise-ish colored line. That's nitrogen. Two more. This is neon. There's a beautiful orange look to it. And when the diffraction grating is in place, you see a large number of red and orange lines. This is exactly what's used for neon lights. The original neon light was made out of neon like this. There are other gases that are used to form signs, but neon was really where it started off. It has a beautiful, bright, reddish orange.
So I have to interject here. That discrete set of wavelengths that you get from each element, or it could be a molecule in the case of nitrogen gas, it's related to the energy levels of the particles, the possible energy levels. And now you're really moving into quantum mechanics. So we'll see later that the spectrum of an atom or a molecule can be used to determine a lot of information about the structure of the atom.
Spectrum. So this is hydrogen. It has a reddish cast to it. And when the diffraction grating is in place, you'll see three lines. The farthest from the central image is a red line. That's the hydrogen alpha line. And it is very important in star images. A lot of nebula in the sky have hydrogen alpha line as one of their prominent spectral lines. Then there's a turquoise colored line. Greenish blue is the hydrogen beta line, both from the Balmer series, and we'll talk about those, or have talked about those in class. And then finally, the hydrogen gamma line is a violet line, is generally considered to be the one that's, those three lines are visible in the hydrogen spectrum. Those lines are associated with transitions of the electron.
Yeah, see, I don't know about you, but to me, these both look blue. I believe when he said violet, he was referring to this line. They both look blue to me.
In the hydrogen atom, from a higher state to a lower state. In this case, the second energy level is the final state, and then higher energy levels, it starts from a higher level and goes down to the second energy level to get the Balmer spectrum. That is continuous and emission spectrum.
Here's another beautiful demonstration from the Florence Science and Technical Institute. So these two examples, diffraction of light through a single narrow slit and through a small circular aperture, those are phenomena that we'll look at in the following presentations. In a moment here, he's going to show interference of light from a diffraction grating. So there's the example that we were in it for. We see the multiple diffraction orders for each color. And of course, those angles are different if they depend on the wavelength. And I'll point out here that this demonstration is not being done with laser light. Laser light is coherent light. The light coming out of the lamp that he's using is not coherent light. And I'll defer the definition of coherent for another time. But in order to make that lamp light coherent, it's got to be passed through a series of slits, which you may have observed in the demonstration here. So producing diffraction patterns with non-laser light is doable. It just takes some more effort. And it was done in the 1800s. Now it's very easy to do in a modern classroom laboratory. So we could do this very easily with just a cheap laser and these diffraction slits from a company like Pasco. A minimum of equipment. And did I mention that the process of passing the incoherent light from the lamp through a series of slits, that's called collimation. Let's just watch a few minutes of this guy explaining how you can use your cell phone or the camera on your cell phone and a low-cost diffraction grating to make a budget spectroscope.
Hi, I'm Matt, and in this video I'm going to show you how you can use your spectroscope to actually analyze the spectra of different elements. So in the last video we built our spectroscope and we talked about the fact that you want this slit at the front really, really thin and defined. And there's a few different things I need to mention about that. If you make your slit too wide, you can actually fix it like I have with this one here and just get another piece of paper and paste that over, sticky tape that over the top, just so you've got a really nice defined slit there. If the slit you've cut is already quite nice and thin and defined, now you can actually use your spectroscope. So another thing I'm going to mention is instead of building your spectroscope out of normal paper, which is 80 GSM, 80 grams per square meter, what we want to do is maybe bump that up to about 120. And it just means that when you make the box, it's a bit more sturdy. So what I have here is a high voltage setup with a neon gas discharge tube. And you can see that that discharge tube is vertical. The first thing you want to do is just make sure you can actually use your spectroscope with your naked eye. And you actually want to put this slit in the same plane or orientation as the discharge tube. So you can see that the slit is horizontal there, but my light source is vertical. What I'm going to do now is turn my spectroscope so that it's in the same plane as the actual source, and that's working quite well. I can easily see some lovely first order, and if I look for it, I can also see second order diffraction lines there. And that's a really important test to see if your spectroscope's working, so definitely use it. And then we can move on to the next part, which is using your spectroscope with your mobile phone to actually take some photos of some spectra. So the first thing you want to do here is actually take your phone out of whatever case it's in. My phone's always in a case, so I've just taken it out there. Just place it on the table in front of you there, and you actually want to sticky tape your spectroscope to your phone. So now that we've got our spectroscope built and it's got that nice, really defined slit in the front of it there, we can actually attach this to our phone here. So what I like to do is just have your phone on the bench there and just get some sticky tape ready. I'm just going to use 3 pieces. So we want the spectroscope positioned so that the diffraction grating, all of it, is sitting, as you can see there, the rainbow color there. So the diffraction grating is sitting directly over the actual camera lens there. So I'm just going to put my phone there, and I'm just going to pre-apply the sticky tape. Now, you won't know if you've done this correctly until you actually use the camera on your phone. Okay, so I've got my sticky tape there on my spectroscope, and what I'm going to do now is just line up my phone. And you don't want to put this on a strange angle. You sort of want to line it up with the phone and just make sure it's all square. Then once you think you've got it square, just apply a force with your fingers there. So now you can see that I've got my smartphone with the spectroscope attached, and it juts out there at a bit of an angle, which is perfectly fine. And we're going to use that to analyze the spectra of various gases now. So when you first attach your spectroscope to your phone and open up the camera, you'll notice that you can actually see the slit, and then below it you'll see some bit of an emission spectra there. So this is just from the ambient light in the room, and it depends on what type of light you have in the room as to the spectra you see. But what I'm going to do now is actually show you on the phone how you go through the settings so that you can take the best photo of spectra possible.
Thanks, mate. You can look up the rest if you're interested. What you're looking at here is the spectrum of the light coming from the sun as seen through a spectroscope or spectrometer, which would use a diffraction grating. This image would have been produced in the same manner that you saw in the previous videos. So the spectroscope or whatever instrument was being used would have produced this image one strip at a time, and then they were just stacked on top of each other to make this final image. And what probably stands out to you is these dark lines indicating that certain wavelengths are not arriving here at the Earth from the sun. In fact, those wavelengths are being absorbed. Later in the semester, we'll talk about the fact that the surface of the sun, whose temperature is around 6,000 kelvins, not coincidentally the same as the temperature of a filament in an incandescent light bulb, puts out a quality of light very similar to the light coming out of a light bulb. It's called a continuous spectrum. So all the wavelengths of the visible spectrum are being emitted by the surface of the sun, but a few of them don't make it from there to here on Earth, and that's because they're absorbed by atoms in the atmosphere of the sun. And so when you look at the light coming from any faraway star, the so-called absorption spectrum, like you see here, gives you information about the composition of the atmosphere. You can deduce which atoms are present, atoms or molecules, ionized molecules, are present in the atmosphere of the star. The last thing I'd like to talk about is the so-called resolving power of a diffraction grating or a spectroscope using a diffraction grating. And just to give you some background, let's watch this video also from the FST channel about the so-called sodium line doublet. So the element sodium has an emission spectrum which includes two very closely spaced lines. When we say lines, we're talking about actually those diffraction orders that you would see through the diffraction grating. It's two colors of yellow which are very close together, and depending on which instrument you're using, they may or may not be distinguished. In this case, it's not a diffraction grating. He's actually using a prism-based spectroscope, but the visual is the same either way. So again, this is not a spectroscope based on a diffraction grating. It uses prisms, but you can imagine if the image here were produced by a diffraction grating, you might be looking at the two different m=1 diffraction orders for those two closely spaced wavelengths of yellow light from the sodium. Let's now take up the question of whether or not a particular diffraction grating could resolve those two lines in the sodium doublet. So we don't need to concern ourselves with the details of this diagram here. It's showing how the closely spaced energy levels in the sodium atom account for those two wavelengths which are emitted. So here are the two wavelengths to the nearest tenth of a nanometer. It looks like the difference between them is 0.6 nanometers. Here, they're giving us that value a little more precisely with 3 significant digits, but we'll just call it 0.6 nanometers. And let's consider a typical grating with 1200 lines per millimeter and find out or investigate the question of whether these two lines could actually be distinguished or whether they would just overlap so much that they wouldn't be resolved from one another. To do that, let's first calculate the actual spacing between the lines. So what I've done is take the reciprocal of the number of lines per millimeter. That would be a thousandth of a meter over 1,200 lines. And see how the units now are meters per line? Specifying the number of meters per line really means the spacing between two adjacent lines. So I get this number. Of course, the nm means that you multiply by 10 to the negative ninth. Now that we know the slit separation, let's just use our formula. We're talking about the first diffraction order, so I plug in m equals 1, lambda over the slit separation d. I take the arc sign. Don't forget to check that your calculator is in degree mode if that's what you'd like. If you want your answer to come out in degrees, you better make sure that your calculator is in degree mode. And then let's see how much different the angle is for the first diffraction order for the other wavelength. So this was the lower wavelength. Let's now try 589.6. So the number up top here has to change. So yes, they are diffracted at different angles. The difference is not great. In fact, it's something like 0.06 degrees. That's a pretty small angular separation. So it's possible, depending on the thickness of the lines, that they would overlap and you would not be able to distinguish the two lines in your spectroscope. Here's another way of arriving at that same result. Let's use a little bit of calculus. So we know that this is the relationship between the wavelength of light and the angle at which it's diffracted, at least for the first order. So I've plugged in m equals 1 here. And I'd like to investigate how a small shift in the wavelength, a change in lambda, results in a change in theta. And that's what calculus does for us. It allows us to look at the ratio of the change in two quantities which are related to each other. So we've got this functional relationship here. And what I'm really doing is taking the derivative of lambda with respect to theta 1. But I don't want to use the conventional calculus notation, which is d lambda over d theta, because I'm already using the lowercase letter d for the slit separation, and that would be confusing. So let's go with this alternative delta notation. Now, most of you have taken a couple semesters of calculus, so you know what it means to take differentials. I'm really just differentiating lambda with respect to theta, and then when d theta pops out in my, well, if I take d lambda, d theta would be in the denominator. I could just move that over to the other side. And that's what I've done here. So the derivative of this expression with respect to theta would be d cos theta, but then I would take that d theta, really the differential d theta, and stick that over here on the other side. So now I have a relationship between the change in the wavelength of light and the corresponding change in the angle at which it's diffracted for the first order. I can solve this for the change in the angle, and this allows me to calculate what that change in angle would be. And then we've already seen that it was about 0.06 degrees. Let's see if this formula confirms that value. All I have to do is plug in the difference in the wavelength between those two colors, and I have to choose a particular theta to plug in. So let's assume that we're currently looking at the 589 nanometers wavelength. So we'll plug in 589. I'm sorry, we're not going to plug in the wavelength. We're going to plug in the angle associated with that wavelength. Let me go back a couple slides. We already found this was the angle at which light is diffracted when it's at this wavelength. So I'm going to plug that angle in right here, and then I'll plug in the change of 0.6 nanometers and then figure out what the corresponding change in the diffraction angle is. Now, don't be confused. It's just a coincidence. We've got 0.6 nanometers as the change in wavelength, and we already found that it was 0.06 degrees as the change in the angle. That's purely coincidental. Okay, this is the spacing between the slits in our diffraction grating. And what I find is that the change in the diffracted angle is Uh-oh, 0.001? That's definitely not 0.06. So does the calculus not work? Or did I do something wrong? Or am I not interpreting this number correctly? Well, when you use calculus, typically the angles you're talking about are in radians. This is really the change in the angle in radians. So let's convert that. There are 180 degrees for every pi radians, and so I do get the same number. So we still haven't really answered the question of whether this diffraction grating could resolve those two lines. All we've really found out is the angular separation between the two lines after you've passed the wavelengths, after you've passed the light through the diffraction grating. Now, if we look at this ratio, 0.06 degrees for a wavelength difference of 0.6 nanometers, just throw that into the calculator. That's the same as saying that you can expect an angular shift of 0.1 degrees for every 1 nanometer difference in the wavelength. So if you increase or decrease the wavelength of light going into the diffraction grating by 1 nanometer, you can expect approximately a 0.1 degree shift in the diffraction angle for the first order. So this is just some notation that I'm using for this particular presentation right here. We've already used the symbol delta theta for the difference in the diffraction angle for those two wavelengths. And now I need a symbol for the thickness, the angular thickness of each line individually. So I'm calling that delta. And clearly, if you have any hope of resolving these two closely spaced lines, you need the thickness of each line individually to be less than the angular separation between the centers of the lines. That's our condition. If you have any hope of resolving these two lines, because sometimes they're very close together, then you need the thickness of each line to be less than the separation between the lines. If that's not satisfied, then they're going to overlap and it will look like just one line. So if that were the case, if you were not able to distinguish them, what would you have to change about your spectroscope or your diffraction grating to actually achieve resolution? Well, if we go back, here's the angular separation between the two lines. It depends on the difference in the wavelengths. Well, supposing you have no control over this, because you can't, you can't change the structure of the atoms necessarily. What you could do is decrease the separation between the slits. In other words, have more lines per millimeter, because the smaller d is, being in the denominator, the larger the angular separation of the lines would be. So clearly there's an incentive to manufacture diffraction gratings with smaller and smaller slit separations. Then there's the added benefit that we talked about in a previous presentation, where as you increase the number of slits, the width of the bright fringes also decreases. So you get two benefits there from putting more lines per millimeter in your diffraction grating. First of all of the lines get more spread out, which enhances your resolving power, but also the lines get thinner. Okay, so the last thing here, what you would do to calculate delta theta in any instance. Here I've got my basic ratio expressed in simplest terms. You've got a separation of 0.1 degrees for every nanometer difference in the wavelength. You would just take that ratio and multiply by the actual difference in the wavelength. So in this case, the difference in the wavelength was 0.6 nanometers. So you would take this ratio of 0.1 degrees per nanometer difference, multiply by 0.6 nanometers, and that would give you your 0.06 angular separation after passing through the diffraction grating. So this is not a general formula for the resolving power of a diffraction grating or a spectroscope, but at least you're now familiar with the notion of what it means to resolve two spectral lines with a spectroscope, and you know how changing the lines per millimeter increases your ability to resolve two closely spaced lines.
So basically there's just lines of grooves on this that are reflective and not reflective. So when you just look at this diffractive grating, it's rainbowy. That's because it's diffracting the different white light from around the room and splitting it up into its red, green, and blue components. But what's cool about this is because it's actually just imprints in the plastic here, You could actually imprint this on another surface and it would have the same properties. It would have that same refractive grating on it as long as it's a little bit reflective. And one thing that you can actually make pretty reflective is chocolate. So chocolate has 6 different crystal phases. One of them is the most reflective and shiny, and that's the one we're trying to get here. And in order to get that, you have to temper the chocolate. So you have to not let your chocolate get too hot. You have to keep it at around 45 degrees Celsius. And once you get all your chocolate melted at 45 degrees Celsius, then you drop in some solid chocolate and let it start to crystallize. Okay, I think we've got our chocolate how we want it. Now I'm gonna just pour it on the diffraction grating here, and hopefully it will just imprint the surface on the diffraction grating onto the chocolate. Okay, the chocolate has now cooled. Let's see what this looks like. See if we can actually get a holographic image of this diffraction pattern on the back of the chocolate here. Ooh, look at that. Look how pretty that is. That is so cool. So I've now made a diffractive optical element out of chocolate. Look how pretty that is. So what's cool about this is you see a rainbow on it, but there's actually no dye on it whatsoever. So you can still eat it. Doesn't this just look so good? So it's amazing you can transfer this diffractive pattern onto the chocolate. It makes these colors that aren't actually caused by any dye or anything on the chocolate. It's just due to the reflective pattern on the chocolate.